Hello, Internet. Welcome to Weird Science, vlog number 1. So before we get started, I just kind of want to go through what I want these vlogs to be, sort of. So I've always been a bit disappointed with how detached academic research is sort of from the non-scientific population. I think it's a natural instinct for people to seek out new information about their world. And I think it's unfair that non-scientists aren't as exposed to some of these ideas that are new, either through the ego of scientists, the stigma of research, or it's the inaccessibility of the papers, which is sometimes even purposeful, I feel. I've got to start with a shameless plug for ALU, because that's all I ever talk about right now. So, as you probably have heard from me already, ALU is sort of a conversation network that I'm starting with Mark Chicoria and Mark Johnson. And it's still in private beta, but you can request an invite if you want to participate in the discussion around this video from sean.swanson@alu.net. Yeah, so it's 1:43, perfect time for science. Let's get it going, yeah? Okay, so we're going to be talking about some ideas in this paper by Christopher Jarzynski called Equalities and Inequalities, Irreversibility, and the Second Law of Thermodynamics at the Nanoscale. So if it sounds super intimidating, I wouldn't worry yet. You can see all these sort of scribbles. Clearly, I really don't even fully understand it yet. So we'll go on a learning adventure together. So there's lots of material in this review paper, and we're only going to scratch the surface. But let's start with the super basics. So the field we're studying is called thermodynamics, and it's a macroscopic science, meaning it's sort of at our scale. It deals with systems that are composed of a ton of atoms, and it sort of studies the effects of heat transfer and work on a system. And those are really the only ways of transferring energy into or out of a system. So there are 4 main laws of thermodynamics, but 2 aren't very important to us right now. The first one is the first law of thermodynamics. It's conservation of energy, which you probably learned in high school. Basically, energy can't be created or destroyed. So the second law of thermodynamics is super important to this paper, and it's sort of iconically demonstrated using this isolated gas. So you have the system here, you have a gas inside, there's a little bit of a partition holding it to one side of the system. You have no heat or work, because it's isolated, and you have it in what's called an equilibrium state, which really just means that nothing is changing. So it's just happily sitting there doing nothing. It's super boring, but we remove the partition, we pull it away, and naturally, we think what happened, the gas is going to expand, it's going to fill the container, right? So here you see all the little dots are spread out, sort of, you can see it. So this is a second equilibrium state. We just kind of wait long enough for it to stop changing. So along the way here, conservation of energy is true, the first law of thermodynamics is true, but what really caused it to move this way, to evolve into that? And the answer is the second law of thermodynamics. So the second law of thermodynamics pretty much says that for an isolated system, such as our isolated gas, when it's going to do any changes, such as when you remove a partition, it's going to evolve such that something called the entropy is going to increase until it hits a maximum. And it is a maximum here, and it is a maximum there, here when the partition is there. So what is entropy? I'm sure everyone is asking, and it's a really hard question to answer. The best answer I guess I could come up with is to think about entropy in these 2 states, when actually I think it's only defined in these 2 states anyway. But basically it is the number of ways that your little microscopic guys, like these little molecules, can arrange themselves to come up with a macroscopic, sort of R-scale system properties. So in that sense, it's sort of a measure of disorder, which you might have heard before. And so you can see sort of why entropy is lower in this equilibrium state versus this equilibrium state, because the space is less. So when I say number of ways you can sort of arrange the microscopic components of the system to come up with a macroscopic system, I'm thinking of taking one of those little guys, maybe moving in that direction, and swapping him out with another guy and moving at the same speed, but a different direction. So I would probably see the same macroscopic properties from that little swap. So I could sort of count that as 2 different arrangements. And you can just from the small amount of space here versus the large amount of space there, you can imagine there are more ways to arrange things here and get the same macroscopic state. So naturally, entropy is higher here than there, and so if I were to release this partition, it is going to move such that it goes to higher entropy. So as you can see, I stuck in this sort of arrow of time business. Because really, the second law of thermodynamics is how we can tell which way time goes. If I were to play this movie backwards of this gas expanding, you would tell me it was stupid. It looked dumb. Now, the second law of thermo has been around for a while, but there's still some aspects of it that are sort of on the cutting edge that people don't quite fully understand. And one of them is sort of how this arrow of time comes about. So this process is one that we call irreversible, because if I were to play the movie backwards, it looks dumb. And what's weird is that the motion of these little guys is essentially reversible. Like if I play it backwards and forwards, it looks fine. So that's a little confusing. Here is sort of a thought experiment that makes it seem like it's okay that this sort of macroscopic arrow of time comes out of something that's like reversible microscopically. So you have like a coin, and if I were to flip this coin, assuming it's fair, it has 50-50 chance of being heads or tails. So you'd agree that that is pretty much reversible. If I had one coin and I kept flipping it, I would pretty much get heads or tails half the time each. So if you take an ensemble of these guys, so I gather, say, 16, and I put them all heads, and then I start flipping every single one of them, and I just keep flipping them, and I just keep flipping them, would you agree that it's unlikely for me to reach this state again, and instead I will pretty much consistently stay around this state? I hope you do agree, because that would be correct. So pretty much this is the same thing with the gas. You start from this state and you sort of move irreversibly toward this state. You never really get out of it again. And that all comes out of sort of reversible dynamics microscopically. Alright, so sorry I'm running a bit late, but at least I hope you're finding this entertaining. We're almost at the payoff. So I have two systems here. One of them I'll call macroscopic, and the other I'll call microscopic. And the macroscopic system has a gas that has about 10 to the 23 molecules in it, which is about something we're used to like handling. It's about a mole actually, and it's a shit ton of molecules. And this guy has about, let's say, 3 in this gas, which is not even really gas. And so it's in this setup where it's in a sort of a cylinder, a closed cylinder, and you have work being put into the system by being able to take this piston and sort of push it into the cylinder. And I should draw probably that, because there's not going to be any heat transfer, because we're not even going to worry about that. So the reason we never really observe violations in the second law is because pretty much it's a matter of statistics. With this many molecules in a macroscopic system, so 10 to the 23, pretty much the odds are overwhelmingly stacked against you about seeing any real fluctuation, sort of a statistical fluctuation, away from sort of mean behavior. For example, say I'm in this room now. Pretty much it's that equilibrium state that we saw, the second one. It's possible that all of the molecules in this room could condense into that corner there and suffocate me. But it's probably not going to happen, because it's really, really, really unlikely. Really unlikely. So really that's the main point of the second law of thermodynamics, is in nature pretty much the most probable stuff happens. Makes sense, right? So when we start looking at smaller systems, say like this little 3 molecule system, the statistical fluctuations matter a lot more, or they become more apparent. So the sort of rigid, like prohibitive character of the second law, you can expect it to act a little bit more leniently on a system this small. As an example of how a microscopic system can sort of defy the second law, I'm taking this irreversible process of taking this piston and shoving it really fast into the gas and then pulling it out really slowly. And you can sort of see when I'm pulling out and there's molecules hitting the side of the piston, I can actually sort of soak up some of their energy and actually decrease the energy of the system. Whereas when I'm pushing the piston in, and I get collisions with the particles, I actually impart energy to them, so I can actually increase the system energy. So there actually exist trajectories for all of these particles in the macroscopic system where you would actually get a net decrease in energy of the system by pushing the piston in and pulling it out slowly. And that would be such as if all the particles sort of weren't really heading toward the piston until it was already in, and then they started colliding once it was starting to come out. But you can imagine that that's actually really unlikely, and so pretty much consistently you can expect the system energy to increase. Anytime you do an experiment, the system energy will increase. But the same is not true for the microscopic system. It might actually be somewhat likely that that you're pushing in the piston, pulling it out, will actually decrease the system energy. Whew. All right, that's it. That's the end. That's the conclusion is that time is fuzzy. So as you shrink a system size, it's more and more likely that it is able to violate the second law. And since the second law is how we dictate the direction of time or perceive it, we sometimes can't tell very easily the direction of time. Booyah.